In this video, we'll begin Module 6, Lesson 7 on planarity and colorings. So the topics in this section and the next one will be related to how graphs are drawn. So the question of planarity is, can a given graph be drawn in a plane so that no edges intersect? Certainly it is natural to avoid intersections, but up until now we haven't gone out of our way to do so. And then the next section will be about coloring. Suppose that each vertex in an undirected graph is to be colored so that no two vertices that are connected by any edge have the same color. How many colors are needed? So that's what we'll be doing in Lesson 8. Just a little bit of preview there. And that question is motivated by the problem of drawing a map so that no two bordering countries are colored the same. A similar question could be asked about coloring the edges of a graph. So what is a planar graph? A graph is planar if it can be drawn in a plane so that no edges cross. If a graph is drawn so that no edges intersect, it is a plane graph, and such a drawing is a planar embedding of the graph. So a graph is planar if it can be drawn with no edges intersecting, and if it is drawn with no edges intersecting, then it's called a plane graph, a planar embedding of the graph. So the graph here in figure 1.3 is planar. In example A of the figure, so the figure on the left, it's not drawn as a plane graph, but it is planar, meaning that it could be drawn as a plane graph. And that's what you see in part B, the same graph drawn as a plane graph. So a couple of notes here. In discussing planarity, we need only to consider simple, undirected graphs with no self-loops. All other graphs can be treated as such, since all of the edges that relate any two vertices can be considered as one package that clearly can be drawn in a plane. Also, we might ask ourselves, can we think of a graph that is not planar? How would you prove that it isn't planar? Proving the non-existence of something is usually more difficult than proving its existence. And this case is no exception to that rule. Intuitively, we might expect that if a graph is more sparse, it's more likely to be planar, whereas a graph that is more dense is more likely to be non-planar. So we'll have a result, a theorem, that will kind of confirm this intuition. And then the topic of planarity is a result of trying to restrict a graph to 2 dimensions, to a plane. So is there an analogous topic for 3 dimensions? What graphs can be drawn in 1 dimension? So here we have just a brief observation about the answer to this third question. If a graph has only a finite number of vertices, it can always be drawn in 3 dimensions. This is not true for all graphs with an infinite number of vertices. The only one-dimensional graphs are the ones that consist of a finite number of chains, as in the figure that you see here. So this is figure 1.5, with 1 or more vertices in each chain. So a chain would look like these examples in 1.5, or you could essentially lay these out in a straight line. A discussion of planarity would not be complete without mentioning the famous 3 utilities puzzle. The object of the puzzle is to supply 3 houses, A, B, and C, with the 3 utilities, gas, electric, and water. The constraint that makes the puzzle impossible to solve is that no utility lines may intersect, i.e., a planar embedding of the graph in figure 1.6, which we'll see on the next page, and that graph is commonly denoted as K33. So this graph is one of 2 fundamental non-planar graphs. I'm going to switch over to it in just a second, but we need to notice here that we have a theorem, the Kuratowski reduction theorem, which we won't be able to prove, but we want to know this result. It states that if a graph is non-planar, then it contains either K33 or K5. Containment is in the sense that if you start with a non-planar graph, you can always perform a sequence of edge deletions and contractions, shrinking an edge so that the two vertices connecting it coincide to produce one of the two graphs. So this is going to be very important, and we'll see an example of this. Remember that before we determine whether or not a graph is planar, we are allowed to do edge deletions and contractions. But the Kuratowski reduction theorem tells us that if we have a K33 or a K5 within our graph, then it will definitely be non-planar. So the K33 that we're talking about is this graph here that you see in figure 1.6. And we know from previous lecture that we use the letter capital K to denote a complete graph on n vertices. So K sub n would be complete graph on n vertices. And that if it is a complete bipartite graph, then we'll use this double index, like in the case of K33. This graph is bipartite because we can think about the set of vertices that is just A, B, and C, the houses, as one set, and the set of vertices that are the utilities, gas, electric, and water. And then no vertex in the first set, the set of houses, is connected to any other vertex in the set of houses, and no vertex in the set of utilities is connected to any other vertex in the set of utilities, but all of the connections from A gets connected to gas, electricity, and water, B gets connected to gas, electricity, and water, C gets connected to gas, electricity, and water. So it's a complete bipartite graph, and we denote that with the letter capital K, and then these two indices indicating how many vertices in each set. The other graph that would indicate non-planarity is the K5, and I'm just going to remind you what that looks like here. The complete graph on 5 vertices. We can start by drawing just a pentagon, and then because it's complete, we would need all of these connections. So that's your K5. These vertices stand out just a little bit. So this is your K5, your complete graph on 5 vertices, and the other one in figure 1.6 is your K33. So the Kuratowski's reduction theorem tells us that we are allowed to delete edges and contract edges. And after doing this process, if we find a subgraph that is K5 or K33, then the graph is definitely non-planar. A planar graph divides the plane into one or more regions. 2 points in the plane will lie in the same region if you can draw a curve connecting the 2 points that does not pass through an edge. So if we're thinking of a graph, I'll just draw a very simple one here. And this is clearly a planar graph. I've divided the plane into 2 regions because I can think of the region inside the graph. The other region is the region outside of the graph. So I have 2 regions. And a planar graph might divide the plane into more than 2 regions, but it divides the plane up into regions, and we would say that 2 points lie in the same region. Let's say here are 2 points. If I could connect them by a curve that doesn't pass through any edge, then those 2 points are in the same region. So that's what we mean when we say region. One of these regions will be of infinite area. That would be the blue region in the picture that I drew. Again, this is just one example, but you'll always have a region of infinite area because we have a finite number of regions to cut up the plane. Each point on the plane is either a vertex, a point on an edge, or a point in a region. So that's just saying it's either a vertex, the black dots here, or it lands on an edge, or it doesn't land on an edge. So that's all it's saying. Any point in the plane could be classified as one of those three categories. And a remarkable fact about the geography of planar graphs will be the following theorem that is attributed to Euler. So you can see we have theorem 1.7 is Euler's formula, and we're going to get to that in just a second, but before we do, we're asked to do a little experiment here. So first let's look at task 1.1, this experiment. It asks us to jot down a graph and count the number of vertices, regions, and edges that you have. So we draw another box here. This time, I'm going to not only form the box, we'll also connect the corners of the box through the diagonal. And now, I know that I want to count the number of vertices, regions, and edges. So if I just started doing that, I might look at it and think, okay, well, here's 1, 2, 3, 4, 5 regions. And I know I have 4 vertices and 6 edges. And then if I plug them in to the formula v plus r minus e, I would have 9 minus 6 is 3, which is not 2. But I have to be a little bit careful here, because remember, we said we're allowed to rearrange the vertices on any graph. We're allowed to contract and delete edges. So let's say I call this vertex A, vertex B, vertex C, and vertex D. Well, what if I drew this? A here, B here, C here, D here. And if I go back to the original graph that I drew, I can see that A should be connected to B, and B should be connected to D. D should be connected to C. C should be connected to A. A should be connected to D. And then C should also be connected to B. So what I have done is just contracted this edge for this vertex D, kind of pulled it inside, up, 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 and then just passed this other edge that connects C and B. So I contracted that edge just a little bit, and now if I do the same count, I can see that in fact there are only 4 regions here. Maybe I call them 1, 2, 3, and 4. I still have 4 vertices and 6 edges, so when I do the formula, I do in fact find the Euler number of 2. V plus r minus e equals 2. And clearly I was able to draw this as a planar graph. So it is a little bit tricky. We want to make sure that we're careful when we're doing this, because at first glance, it might appear that you have something that's non-planar, or it might appear that you actually have more regions than you have. So what is going to be the easiest thing to do? The easiest thing to do is going to be to apply the Kuratowski's reduction theorem to look for K5 or K33 as a subgraph of our graph. So let's jump into Euler's formula. If the graph G equal to V comma E is a connected planar graph with R regions, V vertices, and E edges, then V plus R minus E is equal to 2. And we prove this by induction on E for E greater than or equal to 0. So if E is 0, then G must be a graph with one vertex, V equals 1, and there is one infinite region, R equals 1. Therefore, V plus R minus E is 1 plus 1 minus 0 equal to 2. So the base case for our induction has proven to be true. Now the induction hypothesis will be to suppose that G has K edges for some K greater than or equal to 1. And additionally, that all connected planar graphs with less than K edges satisfy the theorem. So this will be a strong induction. Select any edge that is part of the boundary of the infinite region and call it E1. Let G prime be the graph obtained from G by deleting edge E1. Figure 9.6.4 on the next page will illustrate the two different possibilities that we need to consider. So we took any edge with part of the boundary of the infinite region and we deleted it. So the two cases will be either now G prime is connected or it has two components, two connected components. So let's see that. Case 1, G prime is connected, we delete this at G1, or G prime is not connected, it consists of two connected components, G1 and G2. So if G prime is connected, as in case 1, then the induction hypothesis can be applied to it. If G prime has V prime vertices, R prime edges, and E prime, R prime regions and E prime edges, then V prime plus E prime, pardon me, this is regions, then V prime plus R prime minus E prime is equal to 2. This is just by the induction hypothesis. And in terms of the corresponding numbers for G, V prime is equal to V because no vertices were removed. R prime is equal to R minus 1 because one region of G was merged with the infinite region when that edge was removed. And E prime is equal to K minus 1 because we assumed that G had K edges, we removed one. So we have K minus 1. So for the case where G prime is connected, we have V plus R minus E equal to V plus R prime plus 1 minus E prime plus 1 equal to V prime plus R prime minus E prime, and that's equal to 2 by assumption. So we've shown that it will hold in the case where G prime is connected. What about if G prime is not connected? If G prime is not connected, then it must consist of two connected components, as we've seen above. We'll call them G1 and G2. Then we can apply the induction hypothesis on each of those two components. And essentially that will complete the proof. So some of the details are left out here, but if you are interested in completing the proof, you're welcome to pause the video at this time and try to work that out on your own. It should be pretty similar to what we just did for the connected case. Okay, we have one more theorem here. This is a bound on the edges of a planar graph. So we've seen a bound before in previous lectures. And what this theorem says is that if a graph G is equal to V comma E and is a connected planar graph with V vertices, V greater than or equal to 3, and E edges, then E is less than or equal to 3V minus 6. So we have to assume that we have greater than or equal to 3 vertices, but otherwise, if that condition is met, then a connected planar graph we'll have this upper bound of 3v minus 6 for the number of edges. So we'll just present an outline of a proof here. We let R be the number of regions in the graph G to start with. For each region, count the number of edges that comprise its borders. The sum of these counts must be at least 3R. Remember, we're working with simple graphs, so making a region by connecting two edges from the same vertices would not be possible. So what are we saying? We're saying that if we have a region, then at the bare minimum, we've got 3 edges involved, because we're talking about simple graphs. If we weren't talking about simple graphs, then perhaps we could have this situation, just 2 vertices and 2 edges. But because we're talking about simple graphs, we know at most 1 edge can connect the 2 vertices. So you can think about trying to form a region from just 2 vertices. That would be impossible. So this is just saying that the sum of the number of edges must be at least 3 times the number of regions. Okay? So then based on this, we can infer that the number of edges in G must be at least 3R over 2. So E is greater than or equal to 3R over 2. With just a little bit of algebraic manipulation, we can claim that R is less than or equal to 2E over 3. Then we'll substitute in 2E over 3 for R in Euler's formula. So Euler's formula was V plus R minus E is equal to 2. But we know that R is less equal to 2E over 3. So V plus R minus E should be less equal to V plus 2E over 3 minus E. So now I'll replace this V plus R minus E by 2 because I know it's equal to 2. So I'll say 2 is less than or equal to V plus 2E over 3 minus E. So just combining the Euler's formula with the inequality that we just found out. So this is 2 is less equal to V minus E over 3. And if I multiply 3 on both sides of my inequality, I have 6 is less equal to 3V minus E, or E is less equal to 3V minus 6 if I subtract 6 from both sides and add E to both sides. So this is exactly the upper bound that was given in the theorem for the number of edges if we have at least 3 vertices. So one implication of this is that the number of edges in a connected planar graph will never be larger than 3 times its number of vertices, because 3 times its number of vertices is larger than 3V minus 6, and 3V minus 6 is larger than E. So E will always be smaller than 3 times its number of vertices. And since the maximum number of edges in a graph with V vertices is a quadratic function of V, as V increases, planar graphs are more and more sparse. That's essentially what this comes down to. So one final theorem that will have a quick proof by contradiction is that if G is a connected planar graph, then it has a vertex with degree 5 or less. So to prove by contradiction, we'll start by assuming that G has at least 7 vertices, because otherwise the degree of any vertex is at most 5. Because we're talking about simple graphs here, the first 6 cases are more or less trivial, so we assume that G has at least 7 vertices. Then we assume that G is a connected planar graph and each vertex has a degree of 6 or more because we want to show a contradiction. So we assume the opposite thing. We assume each vertex has a degree of 6 or more. Then since each edge contributes to the degree of 2 vertices, the number of edges would be greater than or equal to 6b over 2, which is equal to 3b. However, we have this inequality that says that this can never happen, so we have a contradiction. So the result is that we know for sure that if G is a connected planar graph, then it has a vertex with degree 5 or less. So now let's look at a couple of exercises. It says apply theorem 1.11, which was this degree of a vertex of degree 5 or less, to prove that once n gets to a certain size, a complete graph on n vertices is non-planar. Then what is the largest complete planar graph? So if we think about the complete graph on 3 vertices, we have this picture, or the complete graph on 4 vertices. Looks like this. And we already talked about this being a planar graph. The complete graph on 3 vertices is clearly planar. But what we want to notice is that in such a graph, the degree of each vertex is n minus 1, where n is the degree of the vertices. So the degree of every vertex here is 2. And that makes sense, of course, because I have to have a connection to every other vertex, and there are 2 other vertices. And the degree of each vertex here is 3. Again, it's only logical because I have to have a connection to every other vertex, and there are 3 other vertices. So this pattern is going to follow. So we can kind of reason that if we must have a vertex of degree 5 or less, then at the worst, we could be talking about K6. So we'll start by saying maybe at the worst we're talking about the complete graph on 6 vertices. And then that would leave room for the complete graph on 5 vertices, except we know by the Kuratowski reduction theorem that this is non-planar for sure. K4 is here, it's planar. So we're good up to K4. We want to check K6 to see if it's planar. So let's imagine we have 6 vertices. I'm going to call them A, B, C, D, E, and F. And let's say they're connected as follows. Then this is actually homeomorphic to the graph K33 because I can form a partition on the set of vertices. I can let A and E and C be one set of vertices, and F and D and B be another set of vertices. And then if I look at the connections between them, I can see that A is connected to F, A is connected to D, A is connected to B, E is connected to F, E is connected to D, and E is connected to B. Also, C is connected to F, C is connected to D, and C is connected to B. So this is one other representation of K33. which we know by the Kuratowski reduction theorem, is non-planar, and if I have this as a subgraph of my graph, then my graph is also non-planar. And this is a subgraph of the complete graph on 6 vertices, because I could just fill in a few more edges here. And then I have the K6. So K6 is also not planar. So the largest complete planar graph is just going to be K4. Okay, the next exercise asks us to determine if the graph is planar or not. If it is planar, we want to find the Euler number. If it is not, then find a subgraph that is homeomorphic to K33 or K5. And this should be a capital K here. Now we already saw in the lecture why it's probably not advantageous to just jump right in and start trying to calculate the Euler number. In fact, if we do so with both of these graphs, we would initially like to think that these are non-planar graphs. So here, if I just start labeling regions, 3, 4, 5, 6, 7, 8, 9, then I'd find that I have 9 regions. I have 8 vertices, A, B, C, D, E, F, G, and H. And I have, if I count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. Then I would do my Euler formula and I would find 9 plus 8 minus 12 to be 5, and I might initially conclude that this is non-planar. But that would be a mistake because I am allowed to contract edges and wiggle things around a little bit. So let me show you how we can do that. I'm going to keep A, D, E, B. In fact, I'm going to keep as much of the original positioning as possible. You don't have to, but I'm going to, just to make it easier for me to see that I do in fact have the same graph. The issue here with this graph is this big long edge from C to D. That's what's clogging up the works. So I think if I could just kind of slide this edge down, then everything else would be fine. So what I'm going to do is I'm going to say, let me make this F and this C, just swapping their places. But let me see if I can maintain the edges, the connections between the vertices. So I want A connected with G, and G connected with B, D connected with G, D connected with E, and I want A connected with D. Then I want B connected with E, and E connected with H, and B connected with H. I want H connected to F, F connected to C, C connected to H, and then I want D connected to C. So did I get everything? I think so. So now I have a planar graph, and I can compute its Euler number. So I'm going to count 1, 2, 3, 4, 5, 6 regions. I still have 8 vertices. I didn't lose any. And if I've done this right, I should still have 12 edges because I also didn't contract any of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so then if I do my computation, v plus r minus e, I have 8 plus 6 minus 12. That's 14 minus 12. And it is, in fact, 2. Just as the theorem told me that it must be in order for this graph to be planar. Now what about the next one? It says determine if it's planar or not. If it's planar, find its Euler number. If it's not, find a subgraph that's homeomorphic to K33 or K5. Well, this looks an awful lot like what we just saw on the previous page, a subgraph homeomorphic to K33 would look like, this blue thing over here. So I want to see if I can recreate that picture because I have a hunch that we might have a subgraph homeomorphic to K33. So I know that I'm allowed to contract edges. What I'm going to do is contract this edge here between A and L. Just imagine that I'm squeezing A and L together, and I'm just going to lay A right on top of L. And similarly, I'm going to contract this edge and have A on top of B. I'm going to contract this edge, put C on top of D. I want to put E on top of F. G on top of H, and I on top of J. So the result, once I'm finished, should look like A has a direct connection to K, because I just contracted that edge from A to L and laid A right on top of L. So I'm also going to have I, and I put I on top of J, and I'm going to have G, E, and C. And then I have a connection between K and I, because there's no more J, I's on top of it, I's kind of covering it up. I'm going to have a connection between I and G, G and E, E and C, C and A. And then these interior edges, if you will, they didn't go anywhere. Nothing really changed about that. So I still have A directly connected to G, I directly connected to C, K directly connected to E. And as we saw in the previous slide, we can think of this as the complete bipartite graph K33, where we have partitioned the set of vertices into, say, K, G, C, A, I, and E. And clearly we can see A is connected to K, G, and C. Then I is also connected to K, G, and C. And E is connected to K, G, and C. So there's our K33. And so this second graph is very much non-planar. So that is the final exercise in this lecture. So we'll conclude the video here, and then we'll tackle the problem of graph colorings in the next video.